second invited talk from Umang Bhatt from the University of Cambridge and the Turing Institute, who's going to talk about challenges and frontiers in deploying transparent machine learning. And he's on the big screen. So if you can share your screen now.
Great. I hope you guys can all see this. Let me know if you cannot. Hopefully, yes. Be full screen.
That's good.
Great. Brilliant. Well, thank you guys so much for having me. As was mentioned, my name is Umang. I'm a PhD student in the machine learning group at Cambridge. Also spent some time at the Turing Institute and at the Leibniz Center for the Future of Intelligence. Today, I want to talk you through some line of work that we've done here around explainability and transparency. And if you have any questions, feel free to shoot me an email or reach out on Twitter. I'm happy to answer them both online at the end of this discussion, as well as offline. Great. So when we started doing this, great. So when we started working on explainability and transparency, we noticed that there was about a decade of work in explainable AI. So this got us thinking about how are a lot of these approaches that we're observing in the research literature, how are they actually being used in practice? So this brings us to, I guess, our first challenge. It was a paper that we wrote and published at the ACM Conference on Fairness, Accountability, and Transparency. And it was joint work where we tried to actually study this problem. How are these approaches actually used in practice, these approaches to explainability that a lot of you may or may not be familiar with? So there's been a lot of proposals for how you explain your machine learning model's output. And the real question is, how do tech companies and some of these other civil societies actually use these algorithms? So the approach that we took was basically doing 30-minute to 2-hour semi-structured interviews with individuals from these organizations, about 50 from 30 major tech companies that were all members of the Partnership on AI, which brings together civil societies, governments, academic institutions, and tech companies to kind of build, hopefully, in the lofty sense, AI for a better world. And I think one of the things that we noticed is it's very important to have a shared language when going into these types of problems. We all need to make sure we're talking about the same thing when we refer to transparency and explainability. So for all intents and purposes of our research, we define transparency in the following way: providing a stakeholder with relevant information about how a model works. Now that's very, very broad, and that captures lots of different notions of transparency. And let's walk through some that we found out when talking to some civil society organizations and tech companies. For those who are not familiar, civil society organizations might encompass groups like Amnesty International, UNDP, Human Rights Watch, the Future Privacy Forum. These are organizations that kind of fight for human rights and fight for all of our civil liberties, whether it be in lobbying contexts or kind of in interactions with tech companies. So the types of transparency, by that definition of providing relevant information, that encompasses documentation. So some of you may be familiar with the idea of model cards or data sheets that Timnit and Meg and great people at Microsoft have also been working on. Can you provide documentation for how your system works? Now, that works, but I think for some of us who are keen on getting into the crux of the machine learning system, the model itself, documentation really provides you with some understanding of how a system works generally. What is the socio-technical ecosystem in which this model lives, right? That answers a different question, and there's definitely a group of people for which this is a acceptable form of transparency. Another form of transparency that many in this room might enjoy is actually just providing your code, open sourcing your code. Whether you can run it or not is a different story. If there are companies that open source some of their code bases for their large language models, I imagine many in this room would not actually be able to have the compute budget to actually run it, but open sourcing your code and providing that is a form of transparency. It's providing you with some sense of an understanding of how their system was built. Whether that is reproducible or not is a different story, but at least you have access to that. However, there are a lot of individuals for which this type of transparency would be very inappropriate. Any of your end users who are affected by your systems, if you're even a doctor who's consuming the output of a diagnostic system for looking at code, is likely not going to help you in making game time decisions. Right? Another form of transparency that we're seeing a lot more of these days is the notion of disclosure. Right? With the onset of GDPR, there's a lot more scrutiny given to what types of disclosure statements you provide end users with, right? And when you're thinking about these types of disclosure statements, they might be something as simple as, I'm using your data in some way to do some inference on you. We've seen various examples of this pop up. On the topic of disclosure, there's been some very interesting recent work on thinking about certification as another form of transparency. Can you certify that maybe the system has certain properties, or better yet, that the developers or the vendors themselves have certain properties and some ethical norms and standards that they've adhered to, right? So this is disclosure about what kind of system has been built by whom. Both of these forms of transparency that we're looking at here, or these three that I've mentioned so far, somewhat capture the ecosystem in which this model will live, or where an AI system would live. It doesn't necessarily tell you properties of the system. I mean, you might know data distributions from documentation, you might even know performance, but in actuality, it doesn't give you any sense of how the system will work. So this brings us to the form of transparency that I've spent most of my research on, which is explainability, as many of you might be familiar with. Explainability tries to provide you with an explanation for how a system works. And specifically, going back to our, in the same spirit of a shared language, we would call explainability, in our research, we define explainability as providing insight into a model's behavior on a specific data point. Okay, so this is also loose in some sense. I mean, there's a lot of things that fall into this category about how you provide insight into why a decision was made on a particular system. But with this definition of explainability in mind, what I can do is we can actually come up with a set of questions that we want to ask each of these individuals that I just mentioned, right? So the questions we ended up asking, I'll kind of zip through them. They include what types of explanations you're using, who's the audience of your explanation, whether it be research scientists, domain experts, product managers, whoever it is, and then in what context are you actually using these systems, right? How does this inform your dev process and inform any decision makers downstream, or even end users for that matter? So I'm going to kind of go through some of the forms of explanations we found were most popular, and then talk about the stakeholders for whom these explanations were very popular. So the types of explanations that we found were popular were threefold. So the first is feature importance. Many of you might be familiar with this. This is largely like a saliency map is a form of feature importance, right? Because if I tell you what my age, my weight, and my body temperature is, I hope that you use my body temperature were I to ask you if I have a fever. Now, maybe you don't. Maybe you have some omniscient capabilities that no one in the medical world is aware of. But by and large, most people would use body temperature to identify if someone has a fever, right? How can we do these kind of simple sanity checks for these systems? Now, there's lots of really great work that has gone into this, but it's a very popular form of explanation, and it's rather accessible. Many of you in the room might have forked Scott's SHAP repo or Marco's Lime repo, and that's great. I mean, it's written in a really accessible and a sensible way, which allows you to play around with these tools. But it is only one form of explanation, right? Another form of explanation that became very popular is called sample importance. This is largely popularized in the technical community, I guess, with the best paper award at ICML in 2017 from Pangway and Percy, called Understanding Black Box Functions via Influence, Black Box Predictors via Influence Functions. The basic premise of sample importance is I have some training data that I've trained on, and I want to know, given a test point, or given any data point for that matter, which of the other training data points are influential to the test point's inference, right? So if I were to remove a data point, how much would that affect the test point's prediction? This is the basic question you ask. And this is a really interesting problem, right? I mean, it's computationally unfeasible. Unfortunately, their method requires inverting a Hessian, which is a d-cubed operation for the keen, and that's expensive. So it's actually hard to deploy in real time, and we'll talk about that in a second. Another form of explanation that's really popular and has analogous definitions in the credit lending literature in the US is a counterfactual explanation. So counterfactual explanation asks the question, what would happen if I were to change something about my input such that my outcome will change? Okay. So this encompasses a large form of, it sounds like an adversarial perturbation for those who are familiar. And in some sense, I want to know how I can manipulate an input such that I can get whatever outcome I want. Okay. And the beautiful thing about counterfactuals is, as a machine learning expert, what would we say? Well, there's an infinite number of possible changes you can make to an input to change the class. There's a bunch of paths I can follow to go across the decision boundary. And there's been really interesting work out of MPI on actually coming up with like feasibility criteria for this. So I can't tell you to decrease your age by 20 years and come back to me and say, okay, well, if you're 20 years younger, I would have given you a loan. Like, that's not even a sensible adverse notice, according to the Consumer Finance Protection Bureau of the US, CFPB, right? How can you come up with feasible perturbations? So feasible things that you're allowed to change. Okay, change your income by 50,000 and come back to me. And we should see how that goes, right? So who are the stakeholders in these systems? There are a handful that are worth discussing. So the first is executives. You see that there's a large rhetoric that is enjoyed by executives in claiming that their systems are interpretable and explainable, right? Everybody loves to be transparent. Everybody wants to say they're transparent. And we see and we notice largely across the industry that executives are joining the train of explainability and transparency, trustworthy machine learning. But unfortunately, operationalizing on it is very, very difficult. And that's what I would implore this audience to consider, how you can actually take these normative ideas of transparency and fairness and actually turn them into something that will not only affect the day-to-day work and day-to-day research, but also kind of have that impact that all of us want it to have. So executives obviously have a stake at play in transparency and explainability. Engineers, as would be expected, I think that engineers kind of found the ease of use of a lot of the systems to be quite nice. You can very, very easily use these systems that have been made for feature importance very specifically. You can quickly debug your systems this way. And that was enjoyed by people all around. And users themselves are also technically a stakeholder. For those of you who have read any of the explainability literature pre-2000, pre 3-4 years ago, everybody would always open their papers by saying end users care about explainability and transparency. Therefore, we're going to propose this tiny little explainability algorithm, test it out on MECTERC workers, and claim it'll work on end users. Okay, it's a sobering thought, but end users are not shown explanations and forms of transparency to date. And then the third and the fourth stakeholder would actually be regulators themselves. So regulators are right now, for those who are familiar, the EU AI Act is being kind of battled through. There's other ideas pertaining to regulation that are simultaneously providing guardrails for research, but also trying to understand how they can leverage some of the tools that we've built in actually developing regulation to keep people safe from like malicious use of these systems, right? So I won't bore you with anything more, and I'll jump into some of the meat of our discussion, but the findings of this work are threefold. The first is that explainability is primarily used internally for debugging within organizations. So contrary to what you'd observe in the research literature, people are basically just using these systems because they're convenient and it kind of makes sense to use them. The goals of explainability are not necessarily clearly defined within organizations, and that makes for a rather tumultuous experience when trying to operationalize these things. And then there's technical limitations. I mean, some of these explanation methods are not necessarily ready to deploy out the bat, and they're not written in an accessible way. I mean, I think some of the work that Kush Varshney's team is doing at IBM is incredible, where they've built IBM, they've done AIX 360, AIF 360, UQ 360. They're tools to take explainability, fairness, and uncertainty quantification and bring them to the masses by writing well-maintained, well-documented code around it. But again, this is just a start. There's a ton of more work to be done in this space. So I won't jump into detail on these findings, but I'll quickly mention that we did some really interesting interdisciplinary work where we, at the start of the pandemic, or right before the start of the pandemic in Feb 2020, we convened with IBM and Partnership on AI. We convened a bunch of experts. So specifically, we had 33 participants from 5 countries who had various amounts of backgrounds, various domain expertise. And our goal was, can we facilitate some sort of inter-stakeholder conversation around explainable machine learning? So what I'm going to quickly do is just run through some of the questions that had kind of come up. Specifically, I want to be able to discuss with you what I call practitioner-driven research questions. So why do I even do this style of work when interacting with policymakers and sometimes these non-technical experts who have a vested interest in how our systems perform? And I do this because it allows me to ask this form of research question that I would encourage more of you to start asking. How do we ask practitioner-driven research questions where our research questions are motivated by the needs of practitioners in the day? So out of that interdisciplinary discussion that we had, we asked 3 questions. One is, can we provide a methodology for practitioners to evaluate explanations? Because evaluation of explanations is very difficult. Can existing interpretability and explainability tools be used to identify model unfairness? And we'll dive into this today. And then can you quantify how much uncertainty is associated with some of these explanations, because they're really brittle models? So how does that uncertainty kind of affect the explanations that you're given? So these 3 questions all stemmed from discussions with non-technical stakeholders. So I'm not going to go into detail in all of them. So the first one we tackled in an IJCAI 2020 paper. Feel free to read that if you're interested. The second question is one I wanted to dive a little bit deeper into. Specifically, we tackled this in an ECAI paper 2 years ago. And I will set up the premise accordingly. So we were sitting down with some regulators here in the UK, and someone had asked, well, if you know what features are important to your system, then can't you just check if a sensitive attribute, so a demographic attribute, appears in this explanation? So if it has high importance, then perhaps your model is unfair. So that's an interesting proposition. I mean, if race or gender appears in the top of your most important features, then likely you might have an unfair model. And it's a pretty simple, easy way to detect this. But unfortunately, there are vulnerabilities that are proposed by this approach. So we'd never thought of this, but we were able to show and expose these vulnerabilities. So the reason we even care about this problem is, imagine on the right-hand side, you had 3 features in Model A. You had the time spent doing some task, the amount of money you have, and let's say age. And age is a protected attribute under the Fair Housing Act of 1956 in the US. So you're not allowed to use age in making decisions. So here we see some amount of attribution on age, right? And on the left, we have model, on the right, we have Model B. Model B has the same 3 attributes, but it has no importance placed on age. So what we might say is that Model A is fair, and Model A is unfair, and Model B is fair, right? Doesn't have any reliance. So our goal that we set out, rather maliciously, is, can we convert a Model A into a Model B? And how do you go about doing that? Right? So there's been a lot of work on manipulating explanations, and I don't want to claim that we were the first to do that. Great people had worked on actually modifying explanations by doing an adversarial attack on inputs. Huge line of work. Amrata, folks at in Tübingen, and then Dylan Slack and co. Everybody's talked about how do you do attacks on inputs and manipulate your explanation. So an adversarial attack done such that you can manipulate those feature importance scores, right? Juyeon Hyo, who's recently joined us here at Cambridge, she had to come up with this really clever idea of doing an adversarial attack on the parameters such that I can control the explanation. Now, what is an adversarial attack on the parameters? Well, it's exactly as it sounds. I will attack my parameters to get whatever outcomes I want. Pretty straightforward. So our goal will be, how can we downgrade that sensitive attribute via an adversarial attack on the parameters such that we can hide that unfairness, right? The reliance on a sensitive attribute. So I'm going to kind of go through some setup. So imagine if you had a classifier that maps from X space to Y space, and we had an explanation function G, with J being our sensitive attribute, okay? So our goal is to find, and let's say F was parameterized by theta, our goal is to find some perturbation delta such that two things are true. One, both models have similar outcomes for the entire trained data set, okay? And then the second is low target feature attribution. So for the feature of interest, how do you have low importance for that feature? Quite straightforward. What we'll do is we'll set this up as we'll set it up as in this kind of following way. We call this an adversarial explanation attack. You fine tune your model after you've trained, and then all you do is append on what we call like an explanation loss. It effectively is just minimizing the gradients with respect in the direction of the jth feature. Also sensible. Right, and I'll quickly jump to the results. But what we can do is on the left-hand side here, you'll see the rank of the sensitive attribute in importance for a plethora of different explanation methods. Recall, we're only penalizing the first. And then on the right, you'll see the rank post-attack. And what do you notice? You see that we're able to reduce the rank, and statistical significance is met. You can read the paper for details, but we can actually reduce reliance on this feature. And this is quite scary, because what does this imply? That we can decrease the relative importance of arbitrary features. This generalizes across test points, transfers across many explanation methods, and performance does not degrade, right? And we can go back then to their policymaker and tell them, well, actually do not include this in regulation. Do not try to use explainability methods to measure unfairness, because if we, as non-malicious people, perform such a malicious attack, imagine what a malicious actor might do, right? And this kind of information, this kind of dialogue between us and practitioners is kind of what I've become addicted to, right? It allows you to have impact near immediately with the work that you do. So another question that we'd also asked is, how can you quantify how much uncertainty is associated with some of these explanation methods? So we'd kind of worked on this with some friends at Quantum Black, which is McKinsey's data science arm. But I'm going to just jump to the findings. Again, there's details in these papers that for those who are interested, they can check out. Particularly, we find the following fact to be interesting, which might be fun for the Bayesians in the room. On the left-hand side, I've taken the most uncertain data point in my training data set, and I've looked at their sensitive attribute, and then I looked at their explanation scores across multiple models. And what do I notice? That their Shapley value score can vary drastically for models that all perform roughly the same. Okay. And then for points where I don't have much uncertainty, there is not a lot of variance in the Shapley value explanation. Shapley value is just a form of feature importance for those who are unfamiliar. So what does this tell us? This tells us that predictive uncertainty will lead to variance in explanation, which is also quite scary, because that means I can just randomly pick a model which has arbitrary explanations that meet my requirement and use that model, which is quite scary. So what does this also imply? More specifically, uncertainty will degrade the quality of explanations with respect to all metrics, including the metrics that we proposed in our HCHI work from 2020, right? Another rather scary finding. But what does this allow us to do? This allows us to say there are two things that are of interest. One is that this first implication is that you might want to consider, as a practitioner, providing this variance, or providing this distribution of feature importance scores, right? Distribution of what's important to your model. And then for uncertain data, it might not make sense to use feature importance method. So we go out and we devise this other method called counterfactual latent uncertainty estimates, also known as clues. I'll probably allude to this in a bit. But basically, if you had a probabilistic model and you had a certain prediction, it might be appropriate and safe to use existing interpretability methods. But if you didn't have one, perhaps you want to explain the uncertainty. So as you can see, I'm explaining the uncertainty by telling you, well, you can reduce your uncertainty were you to remove that portion of the 6 that's connected, right? And these are this style of research questions that I'd love to see more people ask, and there are lots of great people already asking these kinds of questions. I think that these are the 3 things that I hope that folks in this room can take away. But largely, I think that there's this focus on explainability as the only form of algorithmic transparency. So the title of this talk was Challenges and Frontiers in Transparent Machine Learning. So I've talked to you quite a lot about challenges and told you that we've kind of asked these practitioner-driven research questions and gotten more negative results than we would like. But where can we go from here? So again, one of the things that I've talked about so far is explainability is a very, very popular form of transparency. And is there some way we can move beyond this, right? So we have seen a bunch of communities kind of study this idea of uncertainty as a form of transparency. But can we actually aggregate it into one salient piece? So again, what is uncertainty? Well, uncertainty is people saying AI is going to take over the world, but then us being confidently incorrect about some of our predictions. So what we did is we wrote a paper called Uncertainty as a Form of Transparency. How do you measure, communicate, and use uncertainty? Again, with folks at the Partnership on AI. I'm going to quickly walk through each of these different areas about measuring, communicating, and using. Ideally, measuring, using, and then communicating. So how do you even quantify uncertainty? So I imagine that many in the room don't even need an introduction to something like this. But taking the predictive entropy of your softmax distribution is another way this is one fast, quick way of measuring uncertainty. So if I have equally probable classes for all 1,000 classes, that probably means you don't know what you're talking about, right? If you have very large mean and variance bars or large confidence intervals, it's unlikely that you actually have learned something of significant value, right? So if more specifically, we can also break down, some of you may be familiar with this breakdown, but it's interesting to discuss. We can break down what type of uncertainties at play. So here you'll observe the Moon's dataset, classic dataset used in the machine learning research community, two interlocked moons, each of a different class. And what I've done is we've done Bayesian linear regression here. And I can actually decompose the uncertainty in my model in two forms. One is aleatoric uncertainty, right? Aleatoric uncertainty is induced by class overlap. There's no amount of data that will, of additional data that will cure aleatoric uncertainty issues, right? So in the center plot, you'll actually see that where the two classes overlap, there's this uncertainty that's rather irreducible. Noise uncertainty. And then we have model uncertainty, which kind of captures the idea of how much data I've observed to make confident predictions wherever I was going to make predictions. So sensibly, as you move away from the two moons, you get more epistemic uncertainty. And obviously, for those who are familiar with this, collecting more data in those regions will allow you to reduce your epistemic uncertainty. So it's reducible uncertainty. So these types of decompositions of uncertainty can actually be quite useful. For those who are keen, there are ways to get rid of aleatoric uncertainty, perhaps like adding an additional feature, so you can do some interesting projections and reduce that form of uncertainty. But largely, you can't reduce some forms of uncertainty. You can reduce other forms, but these can be of utmost importance to some stakeholders, both technical and non-technical, in understanding where their uncertainty is coming from. You might even have noise or aleatoric uncertainty coming from noisy sensors. So if you have an EKG scan, we've observed with some of our collaborators that if some of your EKG scans are like, some of the sensors are misplaced on your body, it'll induce aleatoric uncertainty. And that's something that even technical or technicians who are actually administering these EKG tests can actually fix themselves, but they have to be notified that this is aleatoric uncertainty, that you're getting noisy measurements from a sensor. That's not something that is necessarily exposed, but is some property of your model and would be considered algorithmic transparency. So once you've measured it, how do you actually use uncertainty in practice? So there are lots of ways of actually using it. One form is actually like looking at fairness, right? Which is another area of interest of mine. So measurement bias, again, as I'd mentioned, if you're trying to infer, for example, like the sensitive attribute because you were unable to collect it in the domain, in the world, and particularly where you're living and like in the world geographically, that might be considered aleatoric uncertainty. And there's been interesting work from Krishna Gumadi's group on this idea of aleatoric uncertainty and epistemic uncertainty breakdowns with respect to fairness. Epistemic uncertainty would be analogous to what we'd call sampling bias, right? Where I have overrepresentation from some groups and underrepresentation from other groups that might be able to be cured, I use that, say that very clear, very emphatically, if you were to collect more data, right? So measurement bias being analogous to aleatoric uncertainty, sampling bias being analogous to epistemic uncertainty. One of my favorite uses of uncertainty is actually building what I call reject option classifiers. So instead of your assistant trying to help you predict if this is a a bird or a plane, I might provide you with my top prediction, I might provide you with a set valued classifier, or I might very well just defer to an expert who can actually decide, right? And I'm using uncertainty as a threshold of uncertainty to decide when to defer, when to abstain from prediction. The beautiful thing is you've already been interacting with reject option classifiers all your life and you just didn't know. If you ever queried Siri or Alexa, sometimes it might say, I don't know what you're saying, let me search the web. Effectively, you're falling into this trap of, I have high uncertainty, I don't know what you're saying, and I refuse to do prediction, and I'm basically going to abstain. And I'm going to provide you, you're going to fall out into a try and accept block, effectively. On the judgment decision-making literature and psychology side, using uncertainty can also be used as a way of showing your ability as a system, knowing that your system actually behaves in the way you want it to when it has high certainty. Benevolence and integrity, which are other notions in psychology that are of interest as well. Providing uncertainty can help build trust with those who are actually interacting with these systems. And if calibrated, then you have a high integrity system. So if you are confident, I expect you to be accurate. If you're unconfident, I expect you to be. So we also have tried using uncertainty to build prediction sets. I'll quickly run through this. But what is a prediction set? I guess is the first question. Well, I might just have a radiology scan and I have some assistant and I might just provide you with the most probable label. This is usually what happens when we think of many of these systems. Now, what I could do instead is actually provide you with a confidence set that contains the true label with high probability, with some probability you specify. So what is the accuracy of the system? Well, it's 95% because I'm telling you I want a system that's 95% accurate or 99% accurate, and you're going to provide me with sets such that that guarantee is met. This is known as conformal prediction for those who are familiar, and this is like kind of the style of work that we use as the workhorse for taking uncertainty and operationalizing it. So we're the first to actually show these prediction sets to experts. And to our surprise, we can actually get better team performance. So better performance when I provide someone with a set valued classifier instead of a top one valued classifier, or even a top one plus randomized value classifier, which is really promising for this line of work, for actually operationalizing and using conformal prediction at scale. When you're actually developing predictive sets for experts, there are lots of really interesting things to consider. Specifically, you might have various labels that have, costs assigned to them, either they're high risk or low risk. So perhaps you want a set that is small, right, that contains medium risk labels, or you might want to narrow down a set. Like you don't want incoherent sets where you have two high risk labels that are very different from each other. Even though both of them might be true, these kinds of sets might be very difficult. But what this kind of predictive set stuff allows you to do is it allows you to provide actionable uncertainty quantification, and it allows you to shape some of these sets by human preferences and competency. So we're more to come on this. We have some work in the pipeline on this, as well as this work at IJCAD this year. So if you're interested, please do take a look. And lastly, after you've measured and you've used uncertainty in some way, you can communicate uncertainty to people. Communicating uncertainty is probably not a surprise to anyone here. There are, when I was a little kid, I remember looking at these hurricane plots, and I always thought hurricanes got bigger. In actuality, hurricanes don't get bigger. They actually just follow one line through this cone-shaped figure. It's not going to hit the whole eastern seaboard of the US. It's going to hit only a portion of it. And in understanding that, you're actually being communicated uncertainty by our meteorologists since day one, right? There are lots of really intuitive ways of actually providing these types of things. You might have seen fan plots or just standard distribution plots, like where you're looking at error. Another thing about communicating uncertainty that we've done is actually providing, as I'd said earlier, providing you explanations of how uncertainty, where uncertainty lies in input space. So this is a paper that was an oral at iClear 2 years ago or last year. And what we actually do is we say, what is the smallest change you can make to an input while staying in distribution, which means we're using generative models, such that our model will produce more certain predictions, right? So instead of telling you what is important, tell me what is causing your uncertainty, if I may use that word cause lightly for now. So as you can see, for the 6, I can actually observe that that interlocking region is what is causing uncertainty in my system. What do these clues look like? These clues might look like, again, you'll have If you have a zero that's open by accident, closing that zero, making it a little thicker, both help in reducing uncertainty. So this form of explanation is very different. But again, I'm using and communicating uncertainty in an actionable way to you. And you can then use this downstream for active learning, for building better human-machine teams, and so on and so forth. And there's a lot of work in this space if you're interested. So at the end of the day, I hope I've convinced you that there are lots of challenges and frontiers with deploying transparent machine learning. I really appreciate your time and appreciate the offer from the organizers for allowing me to come here and speak today. If you have any questions, please feel free to reach out via email or Twitter. Thank you for your time.